Almost 12 years ago, in March 2024, Java 8 was released, and with it, the Stream API. At the time, it was a fundamentally new tool for processing data streams. I'd like to start with a quick refresher on the Stream API. A stream pipeline starts with a source which creates a stream from a data structure, for example, the stream method of a collection. Then we have, optionally, intermediate operations that transform the stream and its elements, such as filter, limit, map. And finally, we have a terminal operation which collects the elements of the stream, for example, with toList into a list. Now let's take a look at a concrete example. We have a list of words here, which we turn into a stream. When the stream method is called, a so-called splitterator is created internally. A splitterator is something like an iterator, but a splitterator can split itself into two parts, and those can split again, so that the data can then be processed in parallel in a parallel stream. In addition, a splitterator has so-called characteristics. These are properties of the data source that can be used to optimize the stream processing. What that means, I'll show you later in an example. Then we say filter, we want words that are at least 8 characters long. Then we say limit 3, we want at most 3 results. And finally comes the terminal operation toList, and only its invocation actually starts the processing. And it proceeds as follows. This is meant to represent the stream pipeline, and this is the list of elements. The splitterator now pushes the first element, avocado, to the filter stage. That stage checks whether the word has at least 8 characters. It does not, therefore the filter operation does not pass the element on to the next stage of the pipeline. The splitterator pushes the next element, banana, to the filter. That one is also too short and is not passed along. Then comes the third element, cantaloupe. Here, the filter predicate evaluates to true, so the filter passes the element on to the next stage of the pipeline, the limit operation. That stage has an internal counter which starts at 0, and therefore the limit operation knows it hasn't passed any elements on yet. It pushes the cantaloupe to the next stage and increments the counter by 1. The terminal operation toList collects the element into a list. Just like the cantaloupe, the dragon fruit now also passes through the pipeline. The counter of the limit stage is now at 2. The fig is not passed on by the filter, and the grapefruit once again goes through the entire pipeline, and the limit counter is now at 3. What does not happen now is that the next element is sent into the pipeline and rejected by the limit operation. Instead, after passing along the third element, the limit operation sends a signal back to the source indicating that no further elements are needed. And as a result, the remaining elements are not sent into the pipeline at all. And now we come to the main topic of the talk. Here's the stream pipeline from the beginning again. And these intermediate operations are quite limited in terms of selection. The Stream API contains exactly 11 intermediate operations: filter, limit, and map, flatMap, mapMulti, which is a faster flatMap, distinct sorted, skip, takeWhile, dropWhile, and peek. And if you look at the feature requests from the Java community, you'll find many wishes for other operations, especially ones like window or fold. But instead of integrating all these requested intermediate operations directly into the stream interface, the JDK developers decided to take a different approach. They developed an API that allows, on the one hand, us Java developers to implement any intermediate operation we want ourselves, and on the other hand, the JDK developers to implement the most requested operations and make them available with the JDK. And this new API is called Stream Gatherers. Stream Gatherers were introduced as a preview feature through JDK Enhancement Proposal 461 in Java 22 in March last year, exactly 10 years after the introduction of the Stream API. They were reintroduced with JEP 473 in Java 23 and finalized in JEP 485 in Java 24. And now I'll first show you how to use predefined gatherers and afterwards how you can implement your own. In the first demo, we have this list of words and we want to group them into sublists of 3 words each. This is also known as a window operation. I have prepared the word list and we'll turn it into a stream. And now, instead of saying, for example, windowFixed 3, which would require a change to the stream interface, we can say gatherers windowFixed 3, and then collect that into a list and print it out. And here we can see the 3 sublists. Besides windowFixed, there's also a predefined gatherer windowSliding. And that creates sublists of 3 elements, each shifted 1 position to the right. And this pattern, gatherers, might look familiar to you. ToList only exists since Java 16. What we had to write before was collectors to list, or to unmodifiable list to create an unmodifiable list, just like ToList does. And now you can clearly see a gatherer is to intermediate operations what a collector is to terminal operations. This way, JDK developers can gradually add more intermediate operations via the gatherers class without having to modify the stream interface every time. And just as we have always been able to write our own collectors for terminal operations, we can now also write our own gatherers for intermediate operations. A string gatherer consists of 4 components, of which 3 are optional. The mandatory component is the integrator, and that's where we'll start. The integrator is the central component of an intermediate operation that receives an element from the previous stage of the stream pipeline, optionally transforms the element, and then passes 0, 1 or more elements to the next stage of the stream pipeline. And it may also terminate the stream early, as the limit operation does, for example. I'd like to show you how we can develop a gatherer using only such an integrator with 2 examples. One that implements a map operation and one that implements a filter. Integrator is a functional interface with an integrate method. This method receives 3 parameters, a state of type A, which we don't use in the first 2 examples, so you can ignore it for now. The element of type T, this is the element that the previous stage of the pipeline sends to this stage, and a downstream through which we send elements of type R to the next stage of the pipeline. Downstream itself is also a functional interface with a push method. We pass the element to it and it returns a Boolean indicating whether downstream wants to receive more elements. If there's, for example, a limit operation downstream, this would return false once the limit has been reached. Back to the integrate method. This one also returns a Boolean, which indicates to the previous stage of the stream pipeline whether we want to continue processing more elements. If not, we return false, which effectively sends the stop signal that I showed you earlier in the animation. And now we want to write such an integrator for the map operation. First, we need a mapping function. And let's say we'll map a string to its length. And the integrator now has the types void, that is the state that we'll ignore for now, string for incoming elements, and integer for outgoing elements. Integrator. We implement the integrator as a lambda that takes the state, the element, and the downstream. Inside the lambda, that's in the integrate method, we apply the mapping function to the element, which gives us the mapped element. And then we send the mapped element to the downstream. And as you remember, push returns a Boolean indicating whether more elements should be sent, and we forward that value unchanged to the previous stage of the pipeline. This integrator can only return false if the downstream does so. On its own, it would never stop requesting more elements. That's why such an integrator is called greedy. And if we indicate that to the stream pipeline, it can optimize the evaluation for early termination. We do that by wrapping the integrator with integrator of greedy. To finally create a gatherer from this integrator, we use the static method gatherer of integrator. And now we can use this gatherer in a stream pipeline. Up here we have our words list again, and now we say words stream, gatherer, to list, and I'll print it out. And here we see the length of the individual strings. And now we can extract this code into a method named mapping. We can inline the gatherer and the mapping function. And this looks quite elegant now. And here below we have the code for this simple mapping gatherer with just an integrator that maps the element and pushes it into the downstream. We can inline the return value here, and the unused state variable can be replaced with an underscore since Java 22. And if we now make this method generic and replace string with T and integer with R, then we could here use, for example, to uppercase, and we would get a string list then. And if we run the program again, we see the elements mapped to uppercase. With this mapping gatherer, we have implemented exactly the same operation as the map operation of the stream interface. And by the way, you can find this project on my GitHub account. There will be a QR code at the end of the presentation for that. Next, I want to show you how to implement a filter operation using a gatherer. I'll clear everything out and keep only the words list. Now we want to filter all elements that have at least 3 characters. So I write a predicate string length is greater than or equal to 3. And again, an integrator. The status type is void again, since we don't need the state yet. The element type is string, and the downstream type is also string, since a filter passes matching elements through unchanged. We write our lambda again. And now we check if the filter predicate matches the element. That is, if the element has at least 3 characters, then we push it downstream and return the downstream's return value. And if not, we do not push anything into the downstream and simply return true, because we still want to see the next element. We can again wrap this integrator with integrator of greedy, since it can only return false when the downstream does. Then we create a gatherer from it using gatherer of integrator. And then we say again words stream, gather, gatherer to list, and print it out. And here we see all words with at least 3 characters. Again, we can inline this into a method filtering, inline the gatherer, inline the predicate, and here again we have a nice clean piece of code. And we have now built exactly the same functionality as the filter operation of the stream interface. Now we could again make the element type generic here, but I'll skip that for time reasons. You can check that out later in the repository. Here again, we can replace the unused state variable with an underscore and inline the return value. Now back to the slides. That was the integrator, and that was also the most important central component of a gatherer. The other components are used for stateful and parallel gatherers. In the next demo, I'll show you how to create the limit operation that was part of this animation, and it had a counter here to terminate the stream early once the desired number of elements was reached. And it's exactly for this counter that we need the state variable. The one I've been skipping over in the code so far, because the map and filter operations don't need any state. But now for the limit operation, we do. And the state first needs to be initialized, and we do that in the initializer. And I'll show you how to do that in the IDE. The initializer is a supplier that creates an object to hold the state. For counting, for example, an atomic integer works well, and the initializer creates this state object with atomic integer new. Then we write another integrator, and the state type is now atomic integer. For the element type, we'll start using string, which we can later parameterize again, and the downstream type is the same as the element type, because the limit operation passes the elements unchanged to the next pipeline stage. We write the integrator again as a lambda, and now we say as long as the state, the element counter, is less than, here we need a variable, max size. I'll set it to 3 and move it up here. So as long as the counter is less than 3, we push the element into the downstream. Then we increment the counter by 1. And we also need to remember the downstream's return value and return it. And otherwise, if we have reached the limit, we return false, which will terminate the stream. So this integrator can return false by itself, and that's why we must not wrap it with integrator of greedy. Then we create a gatherer, and this time we need to use gatherer of sequential. In the previous demos, we didn't have any state, meaning those gatherers could also have been used in parallel. Now, however, we do have state, so we can only use this gatherer sequentially for now. Later, I'll show you how to parallelize a stateful gatherer as well. And this of sequential ensures that the gather stage of the pipeline is executed sequentially, even if the rest of the pipeline runs in parallel. And here we pass the initializer and the integrator. And now we say again words. Sorry, this must go down here. We say again words stream, gather, gatherer, to list, and we'll print it out. And here we see the first 3 words of the list. And again, we can extract this part into a method, limiting and inline max size and inline the gatherer, and we end up with 3 elegant lines of code again. And with this limiting gatherer, we have implemented exactly the same operation as the limit function of the stream interface. And down here, we could again introduce a type parameter, but I'll skip that for time reasons. Here, of course, we can inline the return value. And here, instead of calling get and then increment, we can just say get and increment. Then we don't need a separate increment, and we can inline the result here. When we later write stateful gatherers that also work in parallel, it's important to know that each thread has its own state. That means that the integrate method is never called from multiple threads with the same state object, at least not at the same time, which in turn means that the thread safety guaranteed by the atomic integer here is an unnecessary overhead. We can avoid that by using a non-thread safe counter instead. For example, we could introduce a local counter class with just a count variable. And then down below, use counter instead of atomic integer. But I'd like to show you a small trick to do this without an extra class, or at least without an explicit one. First, we need to inline the initializer and the integrator. And I'll add 2 comments here to make the code readable again. Now we can replace this with a lambda, and instead of an atomic integer, we can create an object with an additional count method. The state is now no longer of type atomic integer, but it's a so-called non-denotable type, a type without a name. So we have to use a question mark here. And down below, we can access the count variable of the state object. Pretty cool, right? So to summarize, we have an initializer that creates a state object, here with the counter starting at 0. You can make that explicit too. The integrator increments the counter, and once it has reached the limit, it returns false to terminate the stream processing. Now, back to the slides. That was the initializer. The third component I'd like to show you is the finisher. And we need that, for example, to implement the fixed window operation I showed you earlier. As a reminder, fixed window groups the elements of the stream into several sublists of a given size, here 3, where the third list only contains 2 elements, since the stream has a total of 8 elements, which is not evenly divisible by 3. And I'll start with the implementation now, and at one point we'll notice that we can't continue. And exactly when you see why we need it, I'll introduce the finisher. Again, we need a state here, and in this case it's the current sublist. So the initializer is a supplier for a list of strings. And we create this sublist with ArrayList new. The integrator now has as its state a list of strings, as an incoming element a string, and as an outgoing element a list of strings again, because we want to create from individual strings lists of strings. Here's the lambda again. And first we append the incoming element to the current sublist stored in the state variable. Now we check whether the sublist has reached the desired window size. For that we need to define a variable, which I set to 3 and move it up here. So if the desired window size is reached, then we'll send a copy of the list downstream. Then we clear the list so we can reuse it for the next window. And this must be copy of. And we remember the return value of push and return that. Otherwise, if the list has not yet reached the window size, then don't push anything and return true so that we continue receiving elements. This integrator never returns false unless false comes from the downstream, so we should mark this integrator as greedy again. And from that, we create a gatherer again, gatherer of sequential initializer, integrator, and then again we say word stream, gather, gatherer to list, and print the result. And we see only 2 sublists here. The last sublist with the 2 elements is missing in the result. And that is because we do add the 7th and 8th element here with add, but since the last sublist never reaches the target size of 3, this code block is never executed, and therefore the last sublist is never pushed downstream. And that's exactly where the finisher comes into play. The finisher is a B consumer that is called at the end of the stream processing with the current state, the list of strings, and the downstream. And we implement the finisher as a lambda that takes the state and the downstream. And here we say, if the list is not empty, then push it to the downstream, or for consistency, push a copy of it. And then we pass the finisher as a third parameter to the gatherer of sequential method. And the type doesn't match. That's because here we need to use a lower bound. And if I start the program again, we now also see the third sublist with the last 2 elements. Now we can extract all that to a method, windowFixed, inline the window size and the gatherer, and again we have 3 very elegant lines of code. And down here we could parameterize the element type again. We could also work with a non-denotable type again, but we don't have time for that right now. You can take a closer look at it later here in Finisher Demo Complete and Finisher Demo Complete Alternative. And to summarize, the initializer creates an empty list as a state. In the integrator, we add elements to the list. When the list reaches the desired size, we push a copy of it into the downstream and clear the list. Otherwise, we return true because we want to see more elements. And at the end, if the last sublist is not empty, we also push that downstream. And we can inline the return value. Yeah, as I showed you earlier, today we don't have to implement this windowFixed gatherer ourselves, but we can simply use gatherers windowFixed instead. Back to the slides. That was the finisher. The fourth and final component is the combiner, and we need that when we want to run a stateful gatherer in parallel. In a parallel stream, each substream has its own state, and with the combiner, 2 state objects are merged into one during the join phase. I'd like to show you this using a gatherer that sums up all the elements of a number stream. For the state, we'll use a separate class this time, an adder, with an int variable sum. Our initializer is then a supplier of type adder, and it creates a new adder object. Next comes the integrator. The state is of type adder, and both the incoming and outgoing elements are not of type string, but this time of type integer. And here's the lambda again. And now we simply say state sum plus equals element. And we return true because we want to sum up all the elements. And that's all for the integrator. And since it always returns true, we should wrap it into integrator of greedy. Here, we're not yet using the downstream inside the integrator because we only want to send the sum to the downstream at the very end, after we have added up all the numbers. So we can replace the variable here with an underscore. Since we're not writing anything to the downstream in the integrator, we need a finisher to handle that. The finisher is again a B consumer. It takes the state, the adder, and the downstream. And here we have to use the lower bound again. Here's the lambda. This is the state. And the finisher sends into the downstream the sum. And we don't even need the brackets here. Finally, we need, let me show you the slide again. For the circle parts, the combiner that merges two state objects into one. The combiner is a binary operator of the state type, that is adder. And it takes adder 1 and adder 2 and produces a combined state by adding the two partial sums. We still need to define the constructor for the sum up here. Let me say this sum equals sum. Now this part is red. That's because we no longer have an implicit default constructor, so we must define one explicitly, and this one will call the other one with 0. Finally, we need to assemble all the 4 components into a gatherer, and this time we use gatherer of again, initializer, integrator, combiner, and finisher. And now we can process our word lists with a parallel stream, first mapping it to integers using, for example, string length. And then we say gatherer. And since we got only one element, we should use something like find first instead of toList and print the result. And here we see the result, the sum of all the string length. And if we now extract all this code into a method called summing and inline the gatherer, we get a nice short code block again. And you can see that we can easily combine regular intermediate operations like map with a gatherer. To summarize, our initializer creates a new adder, one for each substream. The integrator sums all the elements within each substream. The combiner, I'll place it before the finisher, adds 2 partial sums together, and the finisher sends the final sum to the downstream. Here we can inline the return value. And up here, we need to replace adder with a question mark because the local adder class isn't visible outside the method and it doesn't need to be. Back to the slides. That was the last stream gatherer component, the combiner. With these 4 components, you can now implement any imaginable intermediate operations. But as you already saw in the example of the windowFixed operation, you don't always need to write your own gatherer, because for commonly used intermediate operations, the JDK developers have already done that for us. Specifically, there are the following. windowFixed, we've covered this one in depth today. windowSliding, I also showed you this one at the beginning. Fold combines the elements of the stream step by step to a single element, essentially just like stream reduce. Scan performs what's called a prefix scan. It's similar to false, but here not only the final element is pushed downstream, but also all the intermediate results. And map concurrent executes a mapping operation concurrently using the specified number of virtual threads. With this, you can also map elements in parallel, even within a sequential stream. And we can assume that in future Java versions, and also thanks to open source contributors, additional gatherers will become available. Here are two such libraries, which you can find on GitHub when you search for stream gatherers. I'll also link them for you at the end of the presentation. That brings us to the final topic, the performance and limitations of stream gatherers. First, there are no gatherers for the primitive stream types in-stream, long-stream, and double-stream. That is, this stream cannot be reproduced with gatherers unless we add a boxed and convert the ints to integers, but that would negatively affect performance. At least for now. Hopefully this will change soon with Project Valhalla. Second, stream gatherers do not have access to the characteristics of the stream, so they cannot be optimized based on these characteristics. Also, they cannot specify which of these characteristics they retain, and therefore components in the downstream can no longer be optimized based on these characteristics either. And now I'll show you the example I promised you at the beginning when I was talking about the splitterator and its characteristics. Here we have a list of strings, and we first converted to uppercase using map, and once more using the gatherer we wrote earlier. And here, the first version is almost infinitely faster than the second one. And that's because in the first version, count knows that first, the number of elements in the stream is known, namely it's the same as in the words list, and second, that map doesn't change this number. So the map operation is simply optimized away, and count just returns the length of the list. By the way, you need to be careful if the map operation has side effects, which it shouldn't, but if it does, it would still be optimized away. In the second version, count does not know that our gatherer doesn't change the number of elements, and that's why unnecessarily its integrate method is called for every element. Both points mentioned here apply not only to stream gatherers, but also to collectors. And with that, we have reached the end. Behind the QR code, you'll find all the promised links, and if you're interested in more content from me, usually about new Java features, feel free to check out happycoders.eu or one of the other channels. Thank you very much for your attention. I wish you a great conference day with many more exciting talks.